The Science Basement!
Hello and welcome to the Science Basement podcast, a podcast for people who love all things science. I'm your host Zoé.
And I'm your co-host, Tokir.
I'm really excited today for the episode because after a very long time, we have two researchers from my home department at the University of Helsinki, that is the Institute for Atmospheric and Earth System Research, also known as INAR.
Yes, indeed. Well, it gives me an immense pleasure to introducing our guest for today's episode. We have Dr. Zoé Brasseur and soon going to be a Dr. Matthew Boyer.
Hi everyone. Yes, I'm Zoe. I'm a postdoctoral researcher at INAR. So I study atmospheric particles and specifically ice nucleating particles. So these particles that can form ice crystals and ice clouds in the atmosphere. It's quite an important field because these particles can impact cloud formation and also influence climate in general. And and I focus specifically on particles from boreal environments and polar regions.
Nice. Matt?
Hey guys, thanks for having us today. My name's Matt Boyer. I'm also a doctoral researcher at the University of Helsinki, or INAR, and I focus on aerosol processes that occur in the polar regions. And specifically, I'm looking at natural processes that influence the formation of particles that can then influence cloud processes. And it's especially interesting in these regions because these environments are quite sensitive. So we're interested in these processes there. And they're also quite remote and located far away from sources of particles. So understanding the natural sources of these particles in these regions are interesting for us.
Great. It's good to have you, Zoe and Matt, with us today. And by the way, today is also the 53rd World Environment Day. Toki, did you remember that?
Yeah, I have seen some of the videos, some of the pictures today on
Something
the
on
internet.
social
Yeah,
media
exactly.
regarding the 5th of June.
So,
Yes.
yeah, it's nice
And
actually.
what better way to start the episode than having two people from the Earth and Atmospheric Science System to be with us on the 6th episode of season 5.
Okay, so maybe we can also start from the Zoe.
Sure. Take it away.
So, Zoe, tell us a bit about yourself, from where you have done your undergraduate research and how you started this field.
Yes, so I studied chemical engineering in France. And when I realized that I didn't really want to be an engineer, I decided to do another master focusing more on environmental sciences. This was also in France. And at the end of this master's, basically, I had the opportunity to do a 6-month internship here at the University of Helsinki, so here in Finland. And during that internship, I did some field work in the Boreal forest of Hytjala, this research station that belongs to the University of Helsinki. And so that was maybe how I ended up doing research. And so during that 6-month internship, I did some field work at the research station in Hytjala, so in the Boreal forest here in Finland. And so that's really how I got interested into research and atmospheric sciences in general. And that's how I ended up then continuing for a PhD. And this experience in Hytjala was also the opportunity to meet some researchers, for example, during the winter school in Hytjala, which is quite well known.
Okay, sorry to interrupt you, Zoe, but could you please briefly explain what these Hytjala winter schools are, like what exactly they are doing over there?
So basically, it's an intensive field course where students work on data analysis.
Right.
It's mandatory when you're a PhD student here at the University of Helsinki, but we also have some master students and postdoctoral researchers joining. It's quite intense. You have to do a lot of code writing, analyzing data, but it's also a lot of fun. I think Matt had a lot of fun there.
I had a lot of fun there.
That's nice.
So that brings us to our next guest. That's Matt. And I guess Matt and I also have something in common. I mean, I did my master's in the US and Matt's American. So we have something in common. And anyway, just go ahead and give us a brief introduction of yourself.
Thanks, Sujai. Yeah, so I originally come from the US. I did my undergraduate there at a university called Slippery Rock University in Pennsylvania. And my undergraduate degree was heavily focused on geology. It was an environmental science degree, but there was really a heavy geology focus. and I didn't particularly enjoy my geology courses. And I remember it was during my third or fourth year, I had a course called air pollution meteorology, and it was different than geology. And for me, it was an escape from the geology courses, and I immediately connected with it. And I've been interested in the atmospheric sciences ever since then. After that, I did some technical work, doing some air quality monitoring in Bermuda. And then later, I did my master's in Dalhousie University in Canada, also looking at aerosols and cloud processes. And then, in a roundabout way, I ended up at the winter school in Huhtijala, as Zoe mentioned. And after that, I decided I wanted to move to Finland and do my PhD here with this group.
Oh, that's really cool. Great. So, Zoe, could you start by defining what an aerosol is? Because most of our listeners, I think, do know what an aerosol is, but many of them may not.
Yes, of course. So atmospheric aerosols, or sometimes aerosol particles, they are tiny solid or liquid particles that are suspended in the air, in the atmosphere. So they are always around us. They're constantly floating in the air around us, and they can come from natural sources, for example, dust or sea salt, but also pollen is an aerosol that most people are very familiar with. They can also come from sources that are related to human activities, of course. So, for example, soot, but also microplastic. These days, we hear a lot about microplastic because it does eventually go into the atmosphere. They're very small, much smaller than the size of a hair, for example. Usually, we talk about scales like nanometers or micrometers. So they're really tiny, but despite this, they have a huge impact both on the air quality and the climate. And of course, Matt and I, we look specifically at climate in general. And so these particles, they can, first of all, they can influence cloud formation, and they can also regulate how much sunlight comes to the surface and how much is reflected back into space. So they have quite a huge impact on the climate.
And I mean, as far as I know, these particles basically don't settle under the influence of gravity, right? Aerosols are generally so small that they remain suspended.
It depends. So the biggest will usually settle, also because they will be the heaviest.
Right.
So big dust particles, for example, they will settle, but then the smallest one can travel really far, since we even have Saharan dust events here in Finland, so they can travel several thousand kilometers.
But I mean, settle, it takes a long time for them to settle, even if they do settle.
Yeah, so there is a property we call the settling velocity of a particle, which is based on the size and the mass of the particle. But typically, it's very, very low. They're falling very slowly, and because there's turbulence or winds, it can often keep these particles suspended for up to a week or two at a time.
Yeah, right. Because I remember once when I was having this conversation with my father, and he asked me, he's like, do they settle? I said, they don't settle in the way that you throw a tennis ball and it's just going to fall down.
Right, but they are falling.
But they are falling.
Clouds are always slowly falling.
Falling.
But typically, if there's any sort of updraft or anything happening in the atmosphere, it can cause them to actually lift rather than falling.
Right.
Yeah.
And I think the aerosols start as small as, or I mean, rather I would say the biggest ones are 0.01 millimeters, right? That's where it kind of the range starts.
It's roughly that size, yeah.
That
so
size.
Cloud droplets are on the orders of millimeters.
Okay, right.
So and cloud droplets are technically an aerosol, just a liquid one where a lot of water is condensed onto it.
Right.
But then, typically when we look at dry particles, they're on the order of microns. So So a 10 micron particle or a 20 micron particle is already quite large.
Right. And especially at INAR, people are looking at things that are even less than 1 nanometer now, going down to scale of 0.8 nanometer, 0.9 nanometers. So.
Yeah, we're talking orders of magnitude changes here, where you're talking 3 orders of magnitude smaller.
So that's really fascinating, Zoe. And could you give us a sense of what your research looks like in the field? What do you where all have you done your field work, and what you're measuring? Something a bit about your instruments, maybe.
Yes, so usually during my research and together with Matt, we really focused on understudied environments like the polar region, so for example, the Arctic and Antarctica. And I've also conducted a lot of measurements in the Boreal forest, so here in Finland. And so for the measurements, typically, or to put it in a simple way, we usually try to measure how many particles are in the air, and then we try to get an idea of their sizes, sometimes their chemical composition, or their optical properties. So we could try to understand what they're made of and what are their properties in the atmosphere. So of course, beyond measuring how many particles there are, we are also looking at the specific particles that can form clouds. And for this, sometimes we require special instruments, which can be quite challenging, especially for ice nucleating particles. So the particles that I study specifically, they're quite rare, so it's very challenging to study and to measure physically. And when I mean rare, it's like one particle out of several thousands or millions, depending on the location. So we really need specific instrumentation. And once we have these measurements, of course, so more quantitative information, we try to figure out where these particles came from. And sometimes we can also study how they are transported in the atmosphere. And for example, we are interested in knowing what is the spatial range of their influence and how far they can travel, these sort of things.
Well, that's really interesting story, from the boreal forest all the way to Antarctica and from the lab test to the real clouds. And I especially like how just a few tiny particles in a whole liter of air can have such big effect on something as huge as cloud system. And the idea of connecting the living world with the climate process. And I guess that's also the part of your work too, right, Matt?
Yes, absolutely. So I've focused on looking at natural processes and natural sources of particles, and these are often coming from biological organisms or living things in the ocean surface, for example, or we've even recently discovered that penguins have an influence on these particle formation in Antarctica, for example.
No, penguins. I mean, how? How does that happen?
Yeah, it's certainly interesting when you think about it. It's not something you would expect. But so what we've observed is, so there, like I mentioned, in the surface of the ocean, there are phytoplankton, and these phytoplankton give off gases, and sulfur compounds specifically. One such gas is called dimethyl sulfide, or DMS. And once it's released from the ocean surface into the atmosphere, it can be photochemically changed, which means that basically sunlight can cause it to be oxidized. And then once that happens, you can form sulfuric acid. And sulfuric acid in the atmosphere is known to form new particles. And when I talk about forming new particles, I'm talking about gases interacting with each other. So gas molecules are always moving around, and sometimes they can hit each other and they stick temporarily, and then they evaporate again. When you have a high enough concentration of certain gases, they can hit each other and stick. And they can have a third molecule hit them. So then you have three of these molecules stuck together. And as these molecules continue to hit each other and stick, they can then grow to larger sizes. And we call this process new particle formation, which actually forms particles from the gas phase. And specifically, these sulfur compounds can interact with this ammonia gas that's released from penguin guano. And the ammonia has a stabilizing effect because it's a base, where sulfuric acid's an acid. So this acid-base interaction causes them to be slightly more stable. So they're able to form particles more effectively.
I'll have to interject you for a moment.
Sorry.
What is a penguin guano?
Penguin poop.
Okay, okay.
Yeah. So penguin poop, or penguin guano, as we say, is it's a source of ammonia, as we measured, and this ammonia is a basic gas, whereas sulfuric acid is an acid. So this acid-base interaction makes these temporary interactions more stable, so they're more likely to be together longer so that a third molecule can hit them and stick. So what we've noted is that actually the ammonia gas from penguin guano enhances the formation of particles in Antarctica by up to 1,000 times, which is considerable when you consider there's not many other particles present or not many other particle sources, because Antarctica is quite remote, there's not much pollution, and there's not much vegetation there either.
And the sulfur dioxide, this is the gaseous precursor vapor, right? Which forms sulfuric acid with the water in the atmosphere? Or
Yeah. So Yeah, you're going deeper into the chemistry. So DMS
Right.
is off-gassed, and then DMS oxidizes and gives off SO2, and then SO2 can then interact with either OH or H2O and form sulfuric acid. Yes. There's also other gases called methane sulfonic acid, which is another vapor given off, and that gas is not necessarily great at forming particles on its own all the time, but it can actually be really good at growing particles to larger sizes, where they can then act as a cloud condensation nuclei or a cloud seed for water to condense.
Oh, okay.
Yeah, which I think is where the study becomes really interesting. So once you have these particles that have formed from the gases, Matt also studied if they could eventually grow to sizes large enough that they could act as a cloud seed and then form clouds.
Yeah, it's true. So we were lucky. Sometimes when these processes are happening, they're happening on a very localized scale. So there's just a point source of emissions, and these emissions then you have to be in the right location to capture these emissions. But we were actually quite lucky. So when we were located 10 kilometers away from a penguin colony, and when the winds were blowing from that penguin colony, we could see the clear influence of ammonia. And then there was one specific day where we had favorable winds from this direction. There was enough sulfuric acid and ammonia, and we saw a particle formation. And we were lucky and fortunate enough that the wind didn't change direction, and we were able to track the growth of these particles then up to larger sizes, and then we had direct fog. So we actually saw the influence of these specific particles in the fog formation. So we have this is observational evidence that these particles are actually contributing to cloud formation in this environment.
That's really cool, because a lot of the times you don't see any visual sort of proof for these things, and you only get to know that a new particle formation has happened when you look at the size distribution or other such things. But just a visual confirmation that too this happened in Antarctica, so I guess it would have been quite cool to capture that moment in real time.
Yeah, it was really nice. And I remember on this specific day, we could smell the penguin colony at our measurement site.
Oh, yes.
And, it was 10 kilometers away, but it has a very distinct smell.
I mean, I haven't been to Antarctica, but I've been to enough zoos that have penguins.
Yeah.
And you can clearly smell, the penguin ammonia emission, basically.
Yeah, it's awful. but we were excited this day because we could smell it, and then we were looking at our data and we could see, hey, we have this formation event, so we see this process happening.
Right.
And then later in the day, we saw the fog forming, and I said, I've got to look at this specific day to see if this is somehow related and connected, and indeed it was. And like you mentioned, it's if the wind changes direction or if this is a very localized event, the atmosphere is very dynamic. Things are always changing.
Right.
So, for example, if the wind would change direction, we might have these particles could have blown elsewhere, and then we wouldn't have seen this effect. And in fact, for this specific study, we had about 15 to 20 NPF events, and this was the only one where the conditions maintained stable enough for us to see this.
Yes, you always need a bit of luck in science, as they say.
Yeah, for sure.
So Zoe, since the concentration of these ice nucleating particles are so low, it must be a huge challenge to detect them with the instruments. So can you tell us how you deal with that?
Yes, it's quite challenging. So there is really this huge scientific effort made to develop new instruments to be able to do better measurements of these ice nucleating particles.
Okay.
So for example, I have worked with chambers that we use to simulate cloud formation. So you have to picture quite a big chamber, like a big fridge. And we can play with the temperature and the relative humidity in this fridge. And so basically by going to very low temperatures and very high relative humidity, and then by taking some particles that go through this chamber, we can see if these particles can form ice crystals or not, and count how many, and do further analysis on these particles. So that's one way to do measurements, but this is quite demanding. You always need someone to prepare the chamber, first of all, to make sure that everything is running well. And it's a huge instrument, so you cannot easily take it out in the field. For example, in Antarctica, that would be a huge logistic problem or challenge. Okay. And then the problem when we did these measurements in Antarctica, for example, is that you have really low concentration of particles, so very low amount. And so in that case, it was much easier to use filter measurements. So we can sample for longer times and much larger volumes of air to be able to collect just a few ice nucleating particles and to conduct further analysis. So we would sample filters, and then I had this small instrument that we call a cold stage, and I could do experiments with these and for example, try to investigate at which temperature the ice nucleating particles were active, to try to understand where they were coming from, when there were any, because it did happen that there were none at all, so that was quite challenging as well.
Okay, so when you say filters, what are these filters? They are like literally like paper filters that you were collecting these particles?
Yes, they're called also membranes, so they
Okay.
look like paper filters. They're not made of paper, but
A specialized kind of material, maybe.
yes,
Yeah.
exactly. But visually, it does look like a filter paper, and then you just sample air through these filters and try to collect as many particles as possible by using really high airflows.
And what your instrument that you mentioned, that is basically trying to simulate what happens inside a cloud, essentially.
So for the chambers,
Yeah, for the chambers.
yes, for the chambers, we try to recreate what would happen in clouds or in the atmosphere. So that's why we go
Okay.
to very low temperatures, down to minus 50 degrees. And we can also have very high relative humidity as it would be in the atmosphere.
Nice, nice. I mean, it's pretty cool that you're trying to mimic what's happening,
Yeah.
in up in the clouds inside your lab. I mean, inside your instrument, in fact.
Yes, unfortunately, that's the only way we can count ice nucleating particles, because otherwise, how would you know if a particle can nucleate ice or not? So it's also the challenge with this field of research, I would say, is that we have to find ways to simulate cloud formation on scales that can be used in the field.
Right. So you basically the challenge is to really reach low temperatures inside your instrument.
Yes, and also deal with the low concentration of particles.
And yes. And have there been days when you found nothing in your filters because they are so low? Like there have been days when you have just below detection level, I think, in geek speak.
Yes, during the first campaign that we had in Antarctica, we went to the Finnish station Aboa, which is, I think, approximately 200 kilometers away from the coast of Antarctica. So you're really in the middle of nowhere, quite literally, and quite far from the ocean as well. So that means quite far from all sources of particles that would be related to marine biology, for example.
Mm-hmm.
So we're quite remote from this source of particles, and there is really just glaciers and a little bit of ground where there was the station, but that's basically it. And for this specific campaign, I mostly measured at or below the detection limit of the instrument. So it's kind of like the filters did not contain any ice nucleating particle. Which was quite challenging for me because I really had to question the method and do several tests because I thought it was impossible or very, very, very strange. But it is actually robust. It's just that there were very low concentration of particles, first of all, but also specifically ice nucleating particles. And the filter method I used looks at one specific range of temperature or mode of ice formation. This is where my field gets complicated because there are different ways particles can form ice. And with that one method, so looking at one specific mode of formation of ice, we couldn't find any, but it doesn't mean that there were not particles acting at through different modes.
But still, I mean, what is the active range of these ice nucleating particles? Like how big are they?
So you mean in sizes?
In
or?
sizes?
So it really depends. Usually we believe that the larger particle, the better, because ice will be more likely to condense on a large surface. But there's also been studies looking at much smaller particles, like microorganisms or these sort of things, where the particles are quite small, so we even down to nanometers, and they would still be able to nucleate or form ice in the atmosphere. But overall, I would say that the larger particle, then the more chances that they will be able to form ice, especially if they have or if they provide a solid surface.
Okay.
So dust is the perfect
Ice
particle.
nucleator.
Yes, exactly. Particle to form
Yeah.
ice because it is solid and quite large.
Right,
And
right.
usually people say that the best ice nucleator is ice itself because it's already quite large. It has multiple surfaces.
Okay,
And
that's
so
cool.
it's the perfect site to form more ice.
Yeah, well, I mean, from here, Matt, what about the instrumentation that you have used in your research?
Yeah, so it's funny. Zoe looks at really big particles, and I look at really small particles. So it's the complete opposite end of the spectrum, and we have a different set of challenges altogether.
Right.
So we look at instruments that measure these gases, the gases that can actually form new particles, and then we have instruments that also can tell us the number of molecules of different gas species that are clustered together as a particle is forming. And then we have these instruments that are looking at they count the particles at different sizes. So over time, we can actually see the growth of these particles. And then we also have a cloud chamber in our Antarctic measurements where it simulates liquid cloud formation, which is a completely different process than ice cloud formation, because you want to have a particle that's quite soluble or that likes to behave or likes to interact with water, whereas the ice cloud formation is typically these very insoluble particles. So to have all these instruments together and have them running well when you're in Antarctica and in the field, it's quite challenging because some of them they're quite unique and they're quite temperamental and they like very particular conditions to operate well. And when you're in Antarctica, sometimes the environment doesn't play nice
Yeah.
to you. So it's fun, it's a challenge, but it does require a lot of work to get these measurements going and to see these processes.
So, Matt, you recently wrote a paper for the NPR, right? If I'm correct.
You mean the actual paper where it was published, or you mean the articles?
I read something on NPR
Yeah.
regarding your penguin guano paper. So
Yeah.
I think it was covered by NPR, probably.
Yeah, so I did a live interview with NPR.
Oh, okay.
Yeah, and then they also wrote an article. Yeah.
Great, great.
Yeah.
Yeah. How was that experience?
It's quite interesting. So I think penguins are interesting to people, I think, and everyone likes penguins, and penguins are something that's kind of like that. They don't live here.
Yeah.
So people are quite interested in penguins in general. So because the penguins are influential in the process we measured.
Right.
I didn't specifically choose to study penguins or measure penguins, but they were something local nearby our measurement site that it's influencing the atmosphere. So I have penguin in the title of my recent paper, and because of this, a lot of journalists have been interested in asking questions and reaching out, and it's quite interesting to see because some people, they really understand that what we're trying to say, and some people are just they're trying to ask questions about penguins that I don't know the answer to.
Yeah.
But it's quite interesting to engage with people that are not experts in the field and to hear their questions and to answer their questions. It's a different way of thinking about our research questions and the problems we're trying to address.
Yeah, absolutely, absolutely. And I mean, if penguins get you the eyeballs, I mean, it's fine, right?
Even I feel like they are very decent creature.
Yeah, they're very cute and quite funny. Even the way
Yeah.
they behave, the way they walk, and they will come see you, and then
Yeah.
they'll run away to go swim somewhere. But they're also super dirty, and they really smell
They
really
stink.
bad. It's
They
like
really stink.
something people don't picture when they see photos of penguins. They really, really stink.
Yeah, and a lot of the times, some of the penguins we would see, you expect them to be very clean and very white, but some of them were just
Yellow.
they were brown. Just
Okay, so Zoe, you have done your field work in some of the most extreme places on Earth, for example, from the Boreal forest to the frozen parts of the Antarctica. Do you have any unforgettable, funny, or just plain bizarre story from the field? Maybe a moment when you thought, well, this definitely is not every day of your life.
Yes, I've been thinking about the good experience to share, and I think for me the most maybe memorable or something I remember probably forever was this huge storm that hit us in Antarctica during the first campaign.
Okay.
So the storm was, I think, 10 days long, and we had very, very high wind speed, I think up to 55 meters per second, something like this. So we were talking like a hurricane, I think category 3 levels. So it was extremely windy. So it was even hard to walk outside, and then it snowed, so we had absolutely no visibility. And Matt and I were staying in a building that was maybe 10 meters away from the main station. And at some point, the storm was just so bad that it was almost impossible to see the building 10 meters away. So we had to install a rope so we could just grab the rope and know where to walk to be able to reach the main station, where we had the bathroom and the kitchen and the rest of the team. So that was quite intense. I remember the wind being so strong that it would just pull the goggles out of my face. And it was very easy to fall because the wind would just literally just push you to the side or to the ground. And we had a few experiences where we had to cross with Matt, and we would not be able to see each other, even though we know the other person was right there. So it was quite not really scary because we knew we were safe, but you could really imagine how it could get really scary really fast. Mm-hmm. It lasted quite a long time. The wind was super loud, so it was quite strange to sleep in these conditions. And eventually, when the storm went away, we looked around the station, and there was the Swedish station a few 100 meters away, and we saw that one of their containers had been flipped. And I don't know how much a container weighs, but it's something enormous and super heavy. But the wind had been so strong that it just flipped it on its side. So it made us think about what could have happened because we were sleeping in a container. So
that's horrible.
That was quite the experience. I think we will remember this for some time. And of course, we had to stop some of the measurements because this was just quite dangerous. And we found the box with all our pumps that had frozen over during the storm, and it was just an ice cube with pumps frozen in it.
And Matt, what about you? Any bizarre stories from the field?
I would say there was one time when we were up in the north, and we were on a ship, and you don't really have access to resources, and there was no way people were going to get resources to us. Mm-hmm. And one of the instruments broke, and we had to come up with a solution, and we had to ask around for everyone on the ship to see if they had a supply that we needed, which was a power supply. And we had no authorization from the instrument manufacturer to do this, but we started soldering things onto the actual circuit boards of the computer. You know, we took a multimeter and we were testing, and we're like, okay, it looks like this power supply is broken. Let's just find one and solder it in and see if it works, because otherwise we have no measurement if we don't try. And we tried, and actually it worked. So we revived a dead instrument by just soldering things in without. Usually these are the types of things you consult the instrument manufacturer to make sure it's okay, or they send you a spare part or something like this. But up there, you just have to make do with what you have.
But how did you manage that? I mean, do you have a good background with electrical engineering, or how did you?
No, I mean I've worked with instrumentation a bit, so in this sense I know what to check in some ways, and it seemed like we had a power failure for parts of the instrument, and so we traced it back, and
it was detective job, really tracing down to where the problem was coming from. And I think what's really special with that case is that we were not working with the custom built instrument that we had built ourselves and that we knew really well. It was really like something that you buy from a manufacturer, where you're not. Usually, if there's a problem like this, like Matt mentioned, you just send it back and ask for the experts to check it. And meanwhile, we were opening that relatively big instrument and quite expensive too. So it's something that you don't want to to break further or to mess around. So it was we had to be careful, but it was quite satisfying to eventually understand what was wrong and then to find a way to fix it.
And it took us time. We didn't do it in a couple hours. This was over the course of a week or two maybe, where we were slowly identifying and thinking and coming up, trying to find the parts to fix it.
Yeah, and you have to be really careful as well, because you don't want to mess around too much and
or destroy something.
Spoil something or destroy the instrument.
Exactly. We don't want to break something that's not broken, but if it's already broken and we're trying to find a solution, as long as we know we're not breaking something new, I mean, if it's broken, it's worth taking a risk to try to fix it.
Yeah, exactly. And also, I mean, these scientific expeditions cost a lot of money and cost a lot of taxpayers' money. So we are all doing science, and somewhere there are tax dollars being spent on us and our work.
You want to tell about the polar bear?
Oh, I could tell. Okay, yeah, we could do a polar bear story. So, when we were working up in the Arctic, you have to be careful because there are polar bears there, especially when you're out on the sea ice. So during this campaign, Mosaic it was called, there were always dedicated polar bear guards, and there were always dedicated people up on the bridge scouting with binoculars to see if there were polar bears coming in the distance. And there was one time where a group of people were out on the ice and a polar bear started coming, and there was actually a team of oceanographers that had some instruments in the ocean, like they had a CTD to measure the salinity and the depth of the seawater. And it's not something you can just pull out of the water because it's down maybe 100,000 meters, something like this. So they got the notification that a polar bear was coming, and they were in a canoe, and they were trying to recover the instrument as fast as they could. And it just so happened that by the time they got their instrument back and they got off their canoe and they were walking back to the boat, the polar bear was just coming around the other side of the boat. So it wasn't really a close call necessarily. I mean, there was still some space. They weren't in direct danger, but it's kind of interesting how, depending on what you're doing, you have to just let it go and just jump back to the ship because polar bears are out there and you have to respect them.
Okay.
So with that, it's a wrap. A huge thank you to Zoe and Matt for taking the time out of their busy schedules to step into the basement, pun intended, and share their fascinating work with us. And thank you to all our listeners for tuning into this episode of the Science Basement podcast.
And we hope you enjoyed it as much as we did. And if you have any question, want to learn more, or just feel like sharing some fun penguin facts at your next hangout, check out our website or send us just message. And honestly, after this episode, I feel like I have earned this right to be little confident at the bar tonight, sipping my drink and saying, did you know Antarctic clouds might owe their existence to the penguins?
Also, I mean, as this British poet Percy Shelley wrote in his poem called The Cloud, I silently laugh at my own cenotaph. It's a line that captures the eerie, timeless presence of clouds. And after today's episode, I wouldn't be surprised if a few Antarctic clouds born of penguin chemistry are quietly laughing at us too. With that, please like, share and subscribe our podcast episodes with your friends and family. We are all on your favorite podcast platforms such as SoundCloud, Spotify and Apple Podcasts. And for past episodes, you can also check our website, thesciencebasement.org. Thank you everyone for listening, and until next time, take care and bye.
Thank you for having us. Bye.
Thank you. Bye.
Bye-bye.
The Science Basement!